All right, let's dive into something huge. The actual rules that run our entire world. We're talking about the architecture of invisible forces we depend on every single second of our lives. The world we live in, it just works. It runs on these invisible forces. But what are the rules that are actually governing them? I mean, everything from your phone to the lights above you runs on a set of really elegant, really powerful principles. But what are they? How did we even begin to figure out this secret language of electricity? Well, that's exactly what we're going to tackle today. Okay, so to really get a grip on this, we've got to start at the very beginning, the absolute ground floor. We're talking about the simplest, most basic idea in all of electricity. So, what is a point charge? Imagine you take an object that's got an electric charge and you just shrink it down, smaller, 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 until it has literally no size. It's just a single point in space that has a charge. That's it. It's this perfect, hypothetical atom of electricity. And it's super useful because it lets us figure out the basic rules without getting bogged down by, messy, complicated shapes. And from that simple idea comes the first rule. Now, you've definitely heard this one before, but it is the bedrock of everything else we're going to talk about. It's just this. Like charges repel, opposite charges attract. So simple, right? But unbelievably powerful. So what does this actually look like when you put it into practice? Okay, check out this setup. Let's focus on that charge right there in the middle. See the positive charge on the left? It's pushing it away. And the negative one on the right? It's pulling it in. So the way it's actually going to move, the total force it feels, is the result of this little cosmic tug-of-war happening right there. But wait a second. How do these charges even know the other one is there? How do they feel each other across empty space? Well, they create something called an electric field. The best way to think about it is like an invisible force field, or maybe a web, that surrounds any charged object. And this web basically tells any other charge that comes near it which way to go and how hard to get pushed or pulled. It's the medium that carries the message. Okay, so if we have all this pushing and pulling going on all the time, it begs a really interesting question, right? Is it possible to find a spot where all those forces just cancel each other out perfectly? A place where a charged object could just hang there, totally still? Well, yes, and that state has a name. It's called equilibrium. It's that point of perfect, beautiful balance. And what's key here is that the forces are all still there. They're all still pushing and pulling, but they add up to exactly zero. So the object just stays put. No acceleration. This little setup is a perfect way to think about finding that balance. What we've got here is a rod, and on it there are two fixed positive charges. Now, the one on the left is 3 times stronger than the one on the right. So the big question is, if we put a third movable bead on that rod, where exactly would it have to be to stay perfectly still? Think about it. The bead is getting pushed away by both charges, right? The big guy on the left is shoving it hard to the right. The little guy on the right is shoving it back to the left. So to find that sweet spot, that point of equilibrium, you have to move closer to the weaker charge. Why? Because when you're close to it, its little push can be just strong enough to perfectly cancel out the big push from the stronger charge that's now farther away. It's all a game of balancing distance and strength. All right, so point charges are a fantastic starting point. They get us the basic rules. But let's be real. The world isn't made of tiny hypothetical points. It's made of actual stuff. Rings, spheres, wires. So the next logical question is, how do we take these simple rules and apply them to real physical objects? And this is where we have to take a big conceptual leap. We're moving away from that clean, simple world of point charges and into the much messier, but way more realistic, idea of a continuous charge distribution. Basically, the charge isn't at one spot anymore. It's smeared out over a line or across a whole surface or even throughout an entire volume. I mean, just look at this charged ring. Every single little piece of this ring is its own tiny charge, creating its own little electric field. So if you want to figure out the total field at some point, say right above the center, you'd have to add up the effects from an infinite number of points all along that ring. I mean, how in the world do you even begin to do that? Well, let's call it the brute force way, involves calculus. The strategy is to basically break the ring down in your mind into a bunch of infinitely tiny point charges. You calculate the field from just one of those little pieces. Then you use a bit of cleverness. You notice that because the ring is symmetrical, a lot of the forces are just going to cancel each other out. And then you have to do this really complex mathematical summing process, called an integral, to add up all the little bits that are left over. It works, but man, is it difficult. And all of that difficulty leads to a really important question. If the math gets this complicated, this fast, for something as simple as a ring, there has to be a better way, right? There must be some kind of physicist's cheat code. And you'll be happy to hear there absolutely is. Yeah, that whole process of trying to add up an infinite number of tiny pieces is just, it's too much. It's not sustainable. We really, really need a shortcut, a more elegant way of thinking about the problem. And that shortcut has a name. It's Gauss's law. And honestly, it is a total masterpiece of physical insight. Here's the idea. Gauss's law says, forget about adding up all those individual pieces. Just stop. Instead, I want you to draw an imaginary bubble, physicists call it a Gaussian surface, around the charges you care about. The law then tells us that the total amount of electric field poking out through the surface of that bubble is directly related to one simple thing, the total amount of charge you've trapped inside it. That's it. The key idea is right here. It's not about the total charge everywhere. It's only about the charge you enclose. Anything happening outside your imaginary bubble, for this calculation, it just doesn't matter. It's an absolutely incredible simplification of the problem. So let's look at a case like these two concentric spheres. Trying to calculate the field in that space between them, piece by piece, that would be a total nightmare. But with Gauss's law, it's easy. We just draw our imaginary bubble, a sphere in this case, right in that gap. We ask how much charge is inside our bubble. And boom, the law practically just hands us the answer. It's amazing. And this trick doesn't just work for spheres. Take something like a coaxial cable. The symmetry here is cylindrical, right? So we just use a different shaped bubble. We draw an imaginary cylinder inside. The principle is the same. As long as the shape of your imaginary surface matches the symmetry of the object you're studying, Gauss's law turns what looks like an impossible problem into something incredibly straightforward. It's all about picking the right tool for the job. So let's just quickly retrace our steps on this whole journey. We started out with the most basic idea, the simple point charge. From there, we figured out how to find balance with the concept of equilibrium. Then we leveled up to deal with realistic continuous shapes, which seems super hard, until we found the ultimate shortcut, the elegant and powerful Gauss's law. You see how each idea built on the one before it? We went from a single, simple point all the way to a sophisticated tool that lets us understand the complex systems that power, well, everything, our entire modern world. This is that invisible architecture all around us. And this whole thing leaves me with one last big question. We just saw how finding and using symmetry was like a secret key that unlocked a problem that seemed impossible. So it kind of makes you wonder, right? Where else in the universe might symmetry be a hidden cheat code? What other massive, complex problems are just sitting there, waiting for us to figure out the right kind of imaginary bubble to draw around them?